Using Euler's formula, we can now rederive some trigonometric identities, and I want to try and convince you that it's a lot easier to do it this way than perhaps the way you did it in your trigonometry class. So let's start with a first identity. We know that e to the I x plus y is equal to e to the I x times e to the I y, just from the property of exponential functions. Now let's apply Euler's identity to this equation. So we have the cosine of x plus y plus I times the sine of x plus y from the left-hand side, and that's equal the right-hand side, which is cosine x plus I sine x times cosine y plus I sine y. So from the exponential identity now we get trigonometric identities. Remember that a complex equation is equivalent to two real equations. The real part of the left-hand side equals the real part of the right-hand side. The imaginary part of the left-hand side equals the imaginary part of the right-hand side. So let's start with the real part. So the real part tells us cosine x plus y, the real part of the left-hand side. The real part of the right-hand side then is cosine x cosine y. And then it's not the cross term, which has an I in it, but it's I sine x times I sine y. And we get an I squared, which is minus 1. So this is net minus sine x sine y, which is the well-known addition formula for cosine. Rather easy to derive here. What about the imaginary part of both sides of this equation? So that gives us sine of x plus y on the left-hand side. Now it's going to be the cross terms here. So we can start with the I times sine x cosine y. So the imaginary part there would be sine x cosine y. And then we have cosine x times I sine y, and the imaginary part there is cosine x sine y. And that's the well-known addition formula for sine. Okay, so these are the addition formula identities derived very easily using Euler's formula. Let's look at another identity. We have, for the exponential function, we have e to the I n x is equal to e to the I x all raised to the nth power. So we know that we multiply exponents here. So if we apply Euler's formula to this equation, we end up with cosine nx plus I sine nx, and that would be equal to cosine x plus I sine x all raised to the nth power. So again, we can do the real part equals the real part, the imaginary part equals the imaginary part. We can do it for different natural numbers n. But let's look at an example here. Let's just do the very important case, n equals 2. For that case, then, we're looking at cosine 2x plus I sine 2x is equal to cosine x plus I sine x, and all that expression squared. Okay, so what does the real part equals the real part look like? We have cosine 2x then is equal to the real part here. The real part is going to be the cosine squared plus I squared sine squared. I squared is minus 1, so that's cosine squared x minus sine squared x, perhaps an identity you know already. The imaginary part then would be sine 2x. So that would be the cross term here, which would be twice cosine x sine x. Okay, so those are called the double angle formulas. So these are two identities you might know already. When we did integrals, we used two very important identities. They came from our Pythagorean theorem identity. So we know cosine squared x plus sine squared x is equal to 1. If we look at the cosine 2x equals cosine squared minus sine squared identity, then what can we do here? We can eliminate sine squared by writing it as 1 minus cosine squared, and then we can solve for cosine squared x, and we obtain cosine squared x is equal to 1 plus cosine 2x divided by 2, an identity we use for integration. The other identity that we used eliminates cosine squared x on the right-hand side of this double angle formula. So cosine squared x is 1 minus sine squared x, and that gives us the identity sine squared x is equal to 1 minus cosine 2x over 2. Two very important identities that we call them reduction formula, and we've been using them to do integrals, such as the integral of cosine squared x dx. So let me summarize here. Euler's identity, e to the ix equals cosine x plus I sine x, has given us a powerful way to derive trigonometric identities that maybe we used a more complicated way to derive when we learned trigonometry. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.